can you tell me how magnets are relevant to biomedical imaging?
Magnets play a crucial role in biomedical imaging, particularly in magnetic resonance imaging, or MRI. MRI uses strong magnetic fields to generate detailed images of the inside of the body.
Okay, how about TMS?
Transcranial Magnetic Stimulation, or TMS, is a non-invasive procedure that uses magnetic fields to stimulate nerve cells in the brain. It's often used to treat depression, especially in patients who haven't responded well to other treatments. During TMS, a magnetic coil placed on the scalp generates magnetic pulses that pass through the skull and stimulate specific brain regions involved in mood regulation. TMS is considered safe and has been shown to be effective for many people with treatment-resistant depression.
Yeah, how is it relevant to magnets again?
TMS is relevant to magnets because it uses magnetic fields to induce electrical currents in specific areas of the brain. The magnetic pulses generated by the TMS device can penetrate the skull and influence neural activity, which is how it affects brain function and helps treat conditions like depression.
Can you do much shorter responses? How is, just in one sentence, how are magnets relevant to biomedical imaging?
Magnets are used in biomedical imaging, such as MRI, to create detailed images of the body's internal structures by using strong magnetic fields and radio waves.
Okay, how is a simple magnet relevant to MRI?
A simple magnet is not powerful enough for MRI. MRI machines require strong, precisely controlled magnetic fields to produce detailed images.
So those will be electromagnets, are they?
Yes, MRI machines use powerful electromagnets to create the strong and stable magnetic fields needed for imaging. These electromagnets are essential for producing clear and detailed images of the body's internal structures.
Okay, how can I simulate an MRI machine, say, with 4 rectangular magnets?
Simulating an MRI machine using a rectangular magnet would be challenging because MRI requires a very uniform and strong magnetic field, which is typically achieved by highly specialized superconducting magnets. If you're looking for a basic magnetic field experiment, you might consider using a small permanent magnet. However, keep in mind that it won't replicate the complex and precise environment of an actual MRI system.
Okay, say again, how, just in simple terms, how do I simulate an MRI machine using simple basic magnets?
To simulate an MRI with a simple magnet, you can create a basic setup by using a small, strong magnet to demonstrate magnetic field effects. For a very basic experiment, you could show how the magnet affects small metal objects, or compare how magnetic fields interact with different materials. However, keep in mind that this won't replicate the detailed imaging properties of an actual MRI machine. The key aspect of an MRI is the uniform magnetic field and radio frequency pulses used to create detailed internal images.
Okay, so how would you simulate the basic workings of an MRI machine?
To simulate the basic workings of an MRI machine, you could demonstrate the concept of magnetic resonance. For a simple activity, you could use a handheld MRI model or educational kit that explains how hydrogen atoms in the body respond to magnetic fields and radio waves. You might show how these atoms align with the magnetic field and how radio frequency pulses cause them to emit signals that can be measured to create images. This would help illustrate the fundamental principles behind how MRI imaging works.
Okay, what would you see on the screen?
On the screen, I would display a simple animation or diagram showing how hydrogen atoms in the body align with the magnetic field. Then, I'd show how radio frequency pulses are applied, causing the atoms to emit signals. Finally, I'd illustrate how these signals are collected and processed to create an image, highlighting the concept of magnetic resonance. This would help viewers understand the key steps involved in MRI imaging.
Sorry, say again, what exactly would be visible on the screen?
On the screen, I show an animation illustrating 3 main steps. First, how hydrogen atoms align with the strong magnetic field. Second, how radio frequency pulses temporarily disturb the alignment. And third, how the signals emitted by the hydrogen atoms are collected and processed to form an image. This would help visualize the basic principles behind MRI imaging.
Wait a sec. So what if we wanted to do like a single page web application, interactive web application?
For a single page interactive web application, you could create a user-friendly interface that guides users through the MRI process. You could include 1. visuals and animations showing how hydrogen atoms align with the magnetic field and respond to radio frequency pulses. 2. Interactive controls, allowing users to adjust the magnetic field strength or radio frequency parameters and see the effects on the simulation. 3. Explanatory text and pop-ups, providing insights into each step, helping users understand the underlying principles. This would make the MRI concept accessible and engaging for users.
Yeah, I would actually need to see it. Can you provide a basic prompt? So we haven't experienced JavaScript developer. I want to do it as a single page web application, interactive. How would you ask a senior developer to do it?
Could you develop a single-page, interactive web application that educates users about MRI principles? The app should visually demonstrate how hydrogen atoms align with the magnetic field, respond to radio frequency pulses, and emit signals that create an image. It should include interactive elements where users can adjust parameters and see real-time changes. Please ensure the interface is user-friendly and educational.
Yeah, let's actually try it out. And we have another long prompt that we normally use. Question is, which model? Let's go for Gemini 2.5 Pro for a sec. Yeah, single page, interactive. So we're just using HTML, JavaScript, CSS in a single file at the moment to start with. So we're not using React, TypeScript, Tailwind, CSS, Google APIs. I wanted to work with keyboard, mouse, and touch, educational, interactive, and accurate. Yeah, we would like sonification if possible. And we'll have a play demo. Okay, so we're building an interactive web app to teach MRI principle. Applies the single HTML file. Yeah, interactive. Animated hydrogen atom aligning and processing. We already have a MRI simulator from before. Yeah, it's not very great. Applying main field. Apply RF pulse. Apply gradient. It was some detecting signal. I assume that's the sample within the MRI machine. So we'll have a second version of it. Code will still work. What hopefully is. Mueller. Okay, flip doesn't do anything, does it? Is the demo working? Turning on main magnetic field, applying 90 degrees RF pulse. It's not working, is it? The demo is not working. Can you explain what do you currently see on the screen?
Alrighty, picture this. On the left, it's like a tiny proton party with all these arrows doing a little dance. And on the right, you've got this wiggly red signal, like the record player for their proton party music. It's like a little MRI simulator having a blast.
Okay, so it is an MRI simulator. Are we meant to be able to see the output, the image or something of the sample?
Usually an MRI simulator would show you the final image, but this one seems to be focusing on the basic principles, like the behavior of the protons and the signal they produce. It's more about learning how things work behind the scenes rather than showing the picture.
Okay, I don't think it's working great. Can you tell me what is happening? What B0 is on, B0 on, what ready, press B on to begin. Aligning protons with BO field. Okay. RF pulse. Yeah, it doesn't do much, does it?
It looks like the B0 on button is applying a strong magnetic field, which helps align the protons. Then the RF pulse button sends a radio frequency pulse that interacts with those protons. When the protons relax after the pulse, they produce the signal you see on the right. It's like nudging the protons to make a little noise, and the simulator produces that signal.
Okay, can you look at this one? This one is a previous version of the simulation where we apply main field, apply RF pulse, apply gradient, detect signal, which just flicked there briefly, could barely see it. Can you tell which one of the simulation is better, this one or the previous one we've showed?
Well, the previous simulation seemed better for visualizing the proton spins and the signal directly. This current version has a more complex setup with the gradient, which is important for creating MRI images, but it doesn't clearly show the final image generation. So for understanding the basics, the previous one might be better. This one could be useful for learning about specific components like the gradient fields.
Okay, what's the difference between the blue and the red arrows?
The blue and red arrows represent protons in different energy states. The blue ones are usually in a lower energy state, aligned with the magnetic field, and the red ones are in a higher energy state. When the RF pulse is applied, some of the blue protons can jump to the red, or higher energy state.
But is it working as expected? I don't see anything's changing when the field is applied. When we load the page and the field is applied, do you see anything's changing? Is it working correctly or not?
You're right. It doesn't seem to be aligning the protons quite as expected when the field is applied. Based on what I'm seeing, the protons aren't snapping into the alignment with the B0 field the way they should. It looks like there might be a little glitch in the simulation. In a proper MRI sequence, you'd see more of those blue arrows pointing downwards when the main field is on.
Okay, let's check the original prompt. Let's see once.
Okay.
Yeah, so I have this original prompt.
Got it. All right, I have the original prompt again. It seems the simulation isn't quite perfectly aligning the protons with the B0 field as described in the ideal scenario. In a real MRI, most of the protons would align with the field, leading to more blue arrows pointing downwards. The simulation isn't quite showing that strong alignment initially.
Eventually they do seem to align, do they?
Yes, over time, you do see more of the protons aligning with the magnetic field, which is what happens in a real MRI. They gradually settle into the lower energy state, aligning with the B0 field. So the alignment does happen eventually, though it might not be instantaneous in the simulation.
Doesn't an alignment happening much faster considering the strength of the magnetic field?
You'd expect the alignment to happen much faster with a strong magnetic field, almost instantaneous in an ideal scenario. The simulation appears to be slowing down that process, so it's not perfectly representing the immediate alignment you'd expect in a strong magnetic field.
Well, that's a problem in the simulation because then it doesn't actually look like something is happening when the magnetic field is turned on.
You're right. It doesn't make it harder to see the immediate effect of the magnetic field if the alignment is happening so slowly. Ideally, the simulation should show a more noticeable alignment of the protons when the B0 field is turned on. This would better reflect the actual physics of MRI. That sounds like a great way to educate people about MRI principles. I can definitely create a single-page interactive web application for that. It will include visualizations of proton alignment, RF pulses, and signal detection, along with interactive.
So we already used that prompt to generate this web application, but there's obviously some problems with it. Can you actually summarize the prompt and suggest any improvements? Just a quick response.
Sure. The prompt requested a single-page interactive web app to teach about MRI principles, visualizing proton alignment, RF pulses, and signal generation. It needed interactive controls, sonification, and a play demo button. An improvement could be to ensure the proton alignment with the magnetic field appears more immediate and accurate when the B0 field is applied, to better reflect the actual physics.
Okay, so just again in a more critical response, how would you improve this web application that you're currently looking at?
To improve the current web application, it should make the proton alignment with the B0 field appear more immediate and pronounced when the field is turned on, aligning more closely with how it actually behaves in MRI. Additionally, ensuring the simulation accurately reflects the speed of relaxation after the RF pulse would improve the educational accuracy.
Yeah, also everything we do, we eventually publish on biomedical.com.